Not only did Victron just release this awesome new MultiPlus-II 48V 5kVA unit, but here at Current Connected, we have them in stock. Anyway, this thing is absolutely massive for a MultiPlus. However, it's actually quite a bit smaller and lighter weight than the old Quattro 5000. The only difference between this inverter and a Quattro 5000 is the lack of a second AC input, but I think there's a lot of really cool features and advantages this inverter has that makes up for it. Now, while the UL certification for this inverter is currently pending, this does have some of the features we saw when Victron came out with the MultiPlus-II 3000 in the UL 1741 model. And that is an absolutely massive wiring compartment. It's perfect. Now, one of my complaints in the past on Victron MultiPlus inverters is that there's two screws on the bottom of the compartment. And with this one, they've moved them. You can see they're up here on this upper corner instead. That's really nice in the event you put this close to a floor and use, say, Seal-Tight 90 connectors to bring your electrical connections out of here. Now you can actually take the screws out without being at a really awkward angle. So let's pull open this wiring compartment, and you'll notice there is a ton of room in here for activities. I could easily fit my whole lunch in here if I wanted. The first thing that'll pop out to you that is a huge improvement is Victron has gone back to screw down terminals here for the AC in and output connections, which is really nice because on some of their inverters they use spring terminals that are a little bit tricky to get the wire in. You have to use the right size wire, the right strand count, all that good stuff. They have some nice solid screw terminals in here that make it really easy to get your wire in, and these will fit what appears to be 2-gauge wire pretty easily. You may be able to go bigger, but the biggest I would ever try on these is 2-gauge. But let's not forget the DC terminals here on the right. They have a nice beefy bus bar on the positive, and I can see through the holes. It goes straight into the power circuitry. And the negative side doesn't have the same bus bar on it. However, I know underneath the board, there's a little bit of a metallization down here. So it looks like that should be fine too. This is only going to carry about 125 amps peak. So I've got no complaints. They're an M8 thread. You can use a 1/2 inch. It kind of crosses over, but I believe 14 millimeter is your optimal size for that. Moving over to the bottom, we have a power switch here on the right. There's 3 entries here that you can cut off at various different steps depending on your cable size. There's a couple other smaller ones up here that you can use for like your VE bus communication cables, or if you were using any of the auxiliary relays. And then they have 2 entries here and another one here. These look like they're roughly a 1-inch conduit opening knockout in here. I don't totally like these cord grips. They're really designed for SO cord, but if I were wiring this up, I'd probably use like seal-tight conduit instead. I know in Europe, where Victron is originating from, they use cords pretty frequently, but for me, again, I like conduit, but I could easily land a 1-inch conduit on here if I wanted. Now, the one here on the left is probably 1.25 inches. I don't know that I'd really use that. Again, this is rated to output 95 amps if you have AC power available and took advantage of the power assist function. But I think most customers using this would be off-grid. The most they're really going to get out of it is probably 50 amps. And they're probably choosing like a number 6, maybe number 4 at absolute most for their AC output lines. In the wiring compartment, we have a few terminal bars here. If I unplug the terminal strips, you'll see the labeling. This is set up where you can use external ground relays, auxiliary relays, remote temperature and voltage sense, and this little one right here, this 2-pin plug, you can wire into a switch to make a remote power on-off. There's a lot of really cool features you can set up with that. You have your 2 VE bus ports, and they changed the current sense ports. And I know this is starting to come across a lot of the MultiPlus lineup where they're using this 3-wire solution. They used to use what was like one of the old 1/8-inch headphone jacks. However, those jacks occasionally had issues with the contacts inside sticking. So now they're going just to a normal terminal block for the current sensors, and you can use this with an external current sensor. And that's really helpful if you're starting to use some of the ESS features. I have a video on the Victron ESS functionality on my personal channel, so I'll go ahead and get a card in the top corner for that. And now everybody's favorite part of the video, what's inside? Well, there's 4 screws on either side, 2 down here on the bottom, accessible from the wiring compartment. And then this upper blue lid does come off pretty easy. I have had customers repair these inverters in the field before, obviously based on the guidance of Victron, but oh boy is this beautiful. I tell you, this inverter has been one of the hardest ones for me to film because it is so big. I don't think it does it justice on the film. There's a absolutely massive toroidal transformer here at the top. That's because this is a low frequency inverter. And we're going to do some tests here in a minute to see if low frequency still means inefficient. But it's blown me away over time how Victron has simplified the insides of their inverters. If I pan down here to the bottom and get in here on the control boards, there's not a whole lot to them. They have a simple compute board here that sticks up from the main board. They have the power board down here at the bottom that just has some contactors, some current sensors, a big old inductor, and then the H-bridge circuit. But aside from a fan and the transformer, there's not a whole lot in these. And I like that because that usually means there's not a whole lot to go wrong. They've really simplified and consolidated it down here on this one. Now, what better way to test the new Victron inverter than with the new SOK 48V rack mount battery? I've got this hooked up with a set of my 4-gauge Anderson cables. Now, ideally, this inverter, if you were using normal battery cable, you would be using 1/0 cable. However, for my case, I'm just here on the test bench. I'm running a whopping 4 feet between the two, so I should be fine. Now, one thing you guys may have noticed about this inverter, it has very small capacitors. I don't think you guys even saw them because they hide under the H-bridge board. As a result, when I did the pre-charge on this, it charged up very quickly and did not take a lot of regulation. So jumping into it, the power switch is here on the bottom. I'm going to flip that into the 1 position, and here we go, first power up. After a few seconds, it clicked, and I don't even hear a hum. No way. This is super exciting because a lot of these inverters have a hum when they're idling, and that's one of the disadvantages to low-frequency inverters is you get a little bit more noise out of them. And so far, that doesn't seem to be the case. Now, one of the other disadvantages to low-frequency inverters is their idle consumption. So I have my Klein Tools CL800 clamp meter. This one has been all over and back. I'm going to zero it out here. I hope you guys can see that. But it's at 0 amps. Now, this inverter advertises a really low idle draw. It's less than 20 watts. I forget the exact spec, but if we clamp onto this, I have 0.38 amps. Now, these clamp meters are not very accurate at this low of a current rating. So what I'm going to do is actually wrap my cable around here 3 times, and that'll give me 3 times the current reading. So if I measure, that's about right, 0.90. So I have about 0.3 amps. And if I use my fluke meter real quick to measure the voltage, 52.6 volts. So if I calculate that, 52.6 volts times 0.3 amps, that gives me 15.78 watts. Now, me personally, I can't tell you a single inverter that is this capacity, low frequency, that has this low of an idle consumption. So I think Victron really wins the cake on that one. Now let's get into a different test to see if they compromised output power quality just to get this idle consumption down. Because they can always go and modify the sine wave and change the duty cycles on the MOSFETs and that kind of thing to get the idle consumption down, but it's going to affect the output waveform. So let's take a look at that. So as you see here, I've got my 3000 volt differential probe connected on. I have a little tiny piece of solid wire in that terminal strip going to the probe. And since this is a 100% differential probe, I'm just fine to clamp the ground reference to the neutral out of the inverter. And I currently have the differential probe set at 50 volts per division, AC coupled into the oscilloscope. So let's go ahead and power on the inverter, and we'll see the sine wave comes up on here. You can see it's not bad. It doesn't look all that fuzzy. Now, this is a digital oscilloscope, so it does kind of throw you off compared to a traditional analog scope. So you can see there's that little bit of noise right here. I was talking about that little tiny blip. But aside from that, it looks pretty perfect. We can see a little bit of switching noise in here if we really blow it up. But, I mean, this is not anything that's going to make your lights flicker or give you any trouble with your install. I mean, it's pretty dang clean. If I were to compare this to grid power would look worse. The top of this would be cut off, especially here where we're at. We're in an industrial area where there's a lot of loads with poor power factor. So this is pretty much as good as it gets. It's not like they've done anything super crazy. That really is what we wanted to see here on the sine wave, just to make sure they weren't doing anything weird to try and get that idle consumption low in ways that would affect the end consumer. All right, so I went ahead and grabbed the heat gun from the guys in the warehouse. They're not too happy about that. But I wired in a temporary outlet. I have my scope probe here on that. You'll see if I disconnect the wire here. I just frayed the cable I have in there. But this way I can measure the voltage going to the outlet. And I have this heat gun. I forget the rating on this thing. Looks like according to the label it's 1500 watts. So this is only going to be about 20% load. But if I turn it on, it's at full blast right now. And I didn't even notice the sine wave change one bit. That's in cooling mode, so it's just the fan. Let's turn it off and back on again. Back on 1300 degrees. Ooh, yeah, it's hot coming out. That voltage isn't changing one bit. I mean, if I blow it up, yeah, we still have some of those jagged lines we saw before, but all looks really good. I'm pretty impressed by this. You see, it didn't even change at all when that load turned off. So that's pretty impressive. I'm going to call that a pass on the AC sine wave output. This is really beautiful. Anyway, guys, I probably got a little bit crazy on this video, a little too technical, but I'm excited for this. This is an awesome new inverter. This is what we're going to be speccing instead of the Quattros just because it's so much more efficient. And if you calculate that idle draw savings on this, it really pays for itself, and especially the fact that you can simply add an external transfer switch to this. I don't think there's any reason to go with a Quattro 5000 anymore compared to this MultiPlus. So if you guys have any questions, I'm thrilled to hear them in the comments down below. Otherwise, go ahead and hit that subscribe button so we can see you on the next video.